Okay, welcome back. That was sort of a longish video. That's because anytime we do a linear regression analysis, doing the linear regression itself, that is finding our best fit line, is always a very time-consuming kind of process right here. But let's talk about what we call the coefficient of determination and how that relates to what we could say about how closely two variables correlate with one another. In our sum of squares regression, right, we said the total sum of squares, we're going to use some terms right here, the total sum of squares, SST, is the total variation in the observed values from the response variable. In other words, our response variable is y, so every time we get a y value and we take the difference between that and our mean y, right, that's the square of our deviation, right, of each of these y values. We call that a total sum of squares. The regression sum of squares is when we take our predicted value, that is what we got from our equation y hat, right, which is b0 minus b1x, once we actually find that regression analysis, right? Once we do that, then we get that regression sum of squares. We call that SSR. And there's also something called an error of the sum of squares, and that is the variation, the actual difference between what the actual value was in our line and our actual error. And our job, of course, as statisticians, if we're going to use this, is to minimize that error, that sum of squares of error. When we have that minimal sum of squared errors, we actually have the lowest, the best fit line, right? So that's what we're doing. All right. The one we're looking for, the one thing that we're interested in is called a coefficient of determination. We call it r squared. It's small r squared. And it's the proportion of the variation of the observed values of the response variable that are explained by the regression. And we take the sum of squares of our response over the total sum of squares. And when we divide that, we get something called this coefficient of determination, r squared. Right? So we did this in our Excel spreadsheet. Let me show you how I did this with my Excel spreadsheet. Here it is. And in my Excel spreadsheet, you see that we ended up getting SXX and SXY, and that's how we got our equation, right? But now, let's take a look at how we're going to get this determination. So what I did is I carried out the equation a little bit further. So I said y minus y bar. So what I did was I took my y minus y bar squared and I copied that formula down and I got the sum. Which total sum of squares, right? So each one of these observations right here in this column is going to be the sum of squares difference between each y value, the actual y value from the table, and the mean y, right? We square that up. We call that sum of squares of t. Then we get y hat. Y hat is the difference, is the predicted value. So I took my equation, and I'll just show you how I typed this in this first one. I took my equation -3 added to 1, which was my slope, times the x variable. So I go over here to x, which is the x value in my table, and I just multiply that in. And I copied that formula all the way down. So these are the predicted values based on our equation, right? We would, if 7 hours of sleep, we should get a 4. If we have 5 hours of sleep, we should get a 2. If we got 8, we should get a 5, right? If we got 10 hours, we should be happy 7. Of course, we're not, but that's okay. We see what happened. All right. So we take the difference between this predicted value, y hat, and the mean. So y hat minus 4, right? That's this y bar value, squared, and so we get the sum of squares of our predicted, our response variable, right? There it is. And we get the sum of the squares, and that's 16. All right, r squared is the sum of squares, right? Right here, and if we put that in, that means that we're going to take the ratio of sum of squares of regression divided by the total sum of squares, SSR, divided by SST. And there's our sum of squares. Well, this sum of squares, 0.7273, what does that actually mean? Well, let's go back to our discussion right over here. We said that the coefficient of determination is the proportion of variation in the observed values of the response variable explained by regression. Thus, in our response variable for our little table there, we have for our happy mood versus hours of sleep, there's a 72% let's go back to the table here. Let's read this. There's a 72%, right? The proportion of value, observed values explained by the regression. So 72% or 73%, more or less, 72.72%, I guess, of the observed values could be explained by the regression. That's kind of weird, right? There it is. Well, what is that? What is the sum of squares? They did this for another variable, right? And they show you just an observed value of the tables that we have. We have a regression identity. It says the total sum of squares equals the regression of the squares plus the error of the sum of squares. So this is actually how we could get our errors, right? And the sum of squares or errors is actually SST minus SSR. Let me go to my table right here. If I wanted to find my errors, SSE, right? If I want to find my sum of squares or error, what I'm going to do right here is I'm going to take the difference between, let's go back to the table right here, SST minus SSR. SST, which is SST 22 minus SSR, which is 16. So the sum of squares error is 16, right? And maybe another way of thinking about this is that that would be the sum of the squares of the errors that I get from my two different sum of squares right here, right? Okay, well, what does all that mean? What we're talking about right here is that if we have a predicted value of our variable, y hat, right, which is somewhere along this line, for any y hat predicted, right, we might have the observed value. This is our data point up here, right? And then we have our mean observed values, right? So if we take the deviation explained by the regression, that's SSR, and then we get the deviation from the observed value of the mean, so that's SST, then what we get right here, on this piece, is our error, right? So we're actually talking about the error right here, E, between the predicted value and the actual value. And when we take the sum of squares of that error, we're actually getting a variation, right? And we want to get that minimal sum squares of error because that gives us the best fit. All right. If we did this with a much larger data set, we might actually see what that sum of squares of error was, and we could complete this out. But I'm not even going to concentrate on that because we're going to go on to another video, and I'm going to show you what we call the coefficient of correlation and what that means. So stand by.